Well, there's a lot of stuff in this section. We're not done yet, even. And then we have to do a bunch more examples. So hang in there. I'm trying to hang in there, getting all this stuff on the board in a way that makes sense. So over here, I copied the tables, well, the bottom part of the tables. I think I'm running out of ink. What do you think? I got more of these. Let's try this one. Yeah, that's a bit better. So these are the table of critical values, because looking the values up backwards in the regular Z tables, you can't find the exact numbers. And so this gives you, they're still rounded, but they're typical values for 90%, 95, 98. Now, that's what's in the tables at the back of the book. You can find more extensive tables other places. So if you're making this kind of interval, use that kind of critical value. That's kind of nice. And then down here is the formula we're going to be using to make confidence intervals for reference. And then, just for our purposes later, there's the margin of error. It's this thing here. So we call the margin of error what you do, what plus or minus the thing. The thing you're plus or minusing is called the margin of error. And in lots of cases, you try to solve that for n so you can figure out the sample size. So this is sample size for a given margin of error. So you would just say you want to be within 2%. You put 0.02 here, put the stuff in there, and out would come an n that you would use. And you always round up, but that's okay. So there we are. That's background information. And then here's a few confidence interval calculations so you can see how things play out. So this is 90%, so it uses 1.645. This is 95%, so it uses 1.96. This is 99%, it uses 2.58. The number I remember is 2.576, so some strange kind of routing has been going on, but there now it's routed down to 2.58. No big deal. So those are the critical values. Notice they're all approximately 2. Things don't change a whole lot as you go 90, 95, 99. It goes from 1.5 to 2.5. So the interval gets wider. But then if you increase the sample sizes, well, that number goes here. So this multiplies the margin of error. So this thing here, it's the square roots, right? So if this gets multiplied by 100, the square root makes this whole thing get shrunk by a factor of 10. Okay. So if you multiply by 10, you divide by the margin of error is only like about 3 each time you multiply by 10. The square root of 10 happens here. So with 100, with this p hat, when I compute this thing here, I get 0.458. And then if I do 1,000 instead, that gets divided by 3. And if I do 10,000 instead, that gets divided by 3 again. So this number gets divided by 9 as we go down the list, and these just stay about the same size. So that points out the need for large samples if you want accuracy, because no matter what confidence level you're using, you get almost the same size interval. If you really want to change the interval size, you really have to change the sample size. So that's my notes over here. 1, larger n shrinks that, the sigma. So it makes a narrower interval. Larger confidence increases the critical z value. So it makes the interval wider, but not dramatically wider. So because of that not dramatically wider idea, nearly all the confidence intervals people make are this 95% confidence interval, most common, because they're about the same size. And the people who invented confidence intervals said, you know, if you try to be too sure you've got the right answer, then you're looking at an interval that is not that meaningful to people. It's so big, everyone knows the true value's in there. And if you look at one that's higher level of confidence, the interval has to be bigger to be guaranteed to contain the true value. At too small a level of confidence, well, it's not pretty well guaranteed to capture the true value. So if the true value is not in there, you would say, well, could it be in there? Why do we use such a low level of confidence? Why don't we take one that's more likely to capture it? So there's a trade-off. Small confidence level, narrower interval, but the narrower interval is less likely to capture the true value. So maybe not that meaningful to you. Large confidence, big interval, likely to capture the true value, but it might be so big that you go, sure, I knew that already. You're not telling me anything I didn't already know. So somewhere between there is this 95% that seems to have a good chance of capturing the true value, but it's not so big, it's useless, and not so tiny it can't capture it. I don't know. Anyway, that's the suggestion. If no one tells you which kind of confidence interval to make, you make a 95% confidence interval because that is the popular kind, and it is more or less the best kind to make if you don't have any criteria to use. Just make a 95% confidence interval. So if you see a confidence interval displayed with no confidence level attached, it's undoubtedly a 95% confidence interval. If you look at election results and they have a margin of error attached to it and no confidence level listed, those are all 95% confidence intervals. Okay, so we did this. Okay, so now over here, more notes. We can't do this procedure unless we know the sample proportion has a normal distribution. We would like to check NP1 minus P, but we don't have P. We're trying to find out what it is. So we check NP hat times 1 minus P hat is at least 10. This is probably close to this. And so at least 10 is almost the same thing. The second thing is that we said for the sampling to produce a binomial distribution, which then we said would be approximately normal, which then we said we turned into the proportion approximately normal. The sample size should be no more than 5% of the population. So this is true again here. So if you're sampling more than 5% of the population, you'd have to consult an expert as to how do you decide what the margin of error is. So as you sample a larger and larger part of the population, probably your proportion is more accurate than you would think. It's not as random because it's chewing up a lot of the population. And that kind of gets rid of some of the randomness. So probably you could use a smaller margin of error, but you have to consult an expert on that. And then a needed sample size for margin of error, we said this is the formula you're going to use. And you're going to always round up, no matter what. So if this came out to be 31.2, you'd round it up to 32. And that's because 31 would be too small. It won't quite do it. 31.1, if you can make it, will work and give you that margin of error. Anything smaller than 31.1 wouldn't work. So 31.1, you can't use 31, you have to use 32. So the rounding goes anything whole number plus a bit, you go to the next whole number. So I'd say round up to next whole number. If there's any fractional part left, round up to the next whole number. So that's this formula here. Now sometimes you're wanting to carry out an experiment and you don't know what you expect to see for p hat, but you'd like to get a reasonably accurate answer and you want to know what the sample size is. So kind of the worst case scenario for this number, to make n as large as it has to be, is 0.25. So you just take 0.25 times this piece, and that is the largest sample size you'd need to achieve that margin of error with that level of confidence corresponding to a critical value of C alpha over 2. A lot of stuff in the way there, and we got to start banging away at some of these things and using these formulas to create answers to questions, and that's coming up next.